Yeah.
Yeah.
Yeah, that's it. No hope. Okay. Few things from yesterday that we've already went through and stuff like this. This idea of electrons, it's not a visual model, but they're in orbitals. They actually don't orbit in circles. And we saw a little video about that too. We do have these principal energy levels. And they're numbers 1, 2, 3, 4, and so on. They actually correspond to the row that the element is in on the periodic table. The periodic table is a useful thing to just see how things are organized as far as their electron configuration. I'll pause the video just to update more about the periodic table connections as we do a few more of these. Within levels 1, 2, 3, 4, and so on, you may have one or more sub-levels. S is in everything. P starts up level 2. D starts up with 3D. Then you have 4 Fs. And we don't have any letters beyond that for sub-levels, okay? And you can have one or more orbitals. When we were filling in the electron configuration diagrams, we have 3 rules that we use. I don't need you to know them by name, but the Pauli exclusion principle is that an orbital can only have 2 electrons. Then the alpha principle is that you start with the lowest energy and work your way up. Hund's rule is don't pair them up unless each sublevel with equivalent energy orbitals have one in first. I have said don't Google up these things because I'm doing the predicted ones and they may be different than the actual ones. Okay. We looked at a bunch of these and then I left off with 2 for you guys to do. You guys actually chose them. And this is what I hope you have, and I'll pause for a second here. This one, the gold, and then the bismuth. I'll give the bismuth here. So, this is where we left off, guys. Any questions from this? I recorded this too, because the bell was ringing, you probably remember. Yeah? What's that? Okay, scroll up to gold. There's your end result for gold. Okay, now we'll get going. The connection with the electron configuration. I have here, and I went to the page, and I'll thaw the screen. I have here, you guys have this too, so let's define this. There it is. Okay. There's an electron configuration shortcut. I have the outline of the periodic table and some memory aids. Okay. On the periodic table, I've already mentioned this and people retain it. There we go. The row itself is the principal quantum number, the big number 1, 2, or 3. Okay? So that's from the side, 2, 3, and so on. I'm going to pull down this 4, 5, 6, 7. Okay. Those numbers. You just read them directly off. And anything that ends in this zone will end with S's. That's the S orbital zone. Anything from the middle here is the D block. Now I have a -1. Let's see why. So, well, this is, I'm just going on periodic table. You're right. Then this zone over here is the P zone. And then the F zone. Now on yours, I don't think there's a -1 and -2. Is that correct? Do I have -1 and 2? Number -1? Okay, put that down, and I'll explain what it means. I say underneath it, look back at our 4 examples, we'll see how we can give the same information in a shorter form. I'm going to just, so I make it the video, actually, I'm going to bring up a periodic. I'll pause it. Okay, now here's what I'm saying about this shortcut thing. Write the electron configuration for one atom of each element, only use your periodic table as a guide. Now, out of the 4 that we did, then you guys did 2 additional ones. Choose one of those, and I'll go through that first before we try some different. Choose any one of the ones we've done as a diagram. Someone. I don't care which one. Okay, I'll choose one. So I'm going with this. Let's go with tin, SF, okay? So we're keeping this in mind. S block, D block, P block. Now this -1. That's about the front number, the principal quantum number, and -2 for this. So tin. Let's find it on the periodic table. You guys have this handout in front of you, but I'm going to switch screens because of the video. There we go. SF. So what I'm talking about here is SF. Sorry. If you recall from your outline box, because you have it, this is the S block, these are the D's, these are the P's, these are the F's. I said -1 for these, -2. Now, what am I talking about there? Well, if you want to do tin without that chart to tell you S's and P's and 3B and 4F and stuff like this, here's what we're going to do. We're going to use the periodic table, and we always start with the previous row's noble gas because it has all the electrons. And you've done this one, so I just want you to pencil down and watch. So for tin, I'm going to say krypton is the shortcut, KR. Then I would say tin is in, and I'd say right here, level 1, 2, 3, 4, 5. So I'm going to start with 5, and this is the S block, these 2 columns. S1, 2, 5. My 5 looks like an S, so I'm going to rewrite it. 5, S, and 2. Then I count through these. There's 10 of them in this D zone. But I have that -1 as a memory. If I start with level 5, because it's in the fifth row. By the way, the words row and column. Rows are left to right, columns are up and down. I take whatever row I'm on, so in this case 5, and I subtract 1 from it for the front number of the D block, the principal column. So I say -1, that's 4. D, and it's 10 across, and I still haven't gotten to 10. Now, the P is the same front number, even though D went down. So I go back to 5, level 5, P, 1, 2. Okay? This is how you do it without that chart. What's that? What else? Curricular reasons. For curricular reasons. I don't make them. Yeah, well, that's not, it's out of my hands. Okay? So, I'm going to just not erase that. So we're going to do 1 or 2 of these. And see about this shortly. So we're going to do the electron configuration for one atom of these elements: aluminum, bromine, radon. So you got your periodic table. I'm going to do it on this one, so just so we can keep track and keep it. Okay, aluminum, bromine, radon. So aluminum. Start something a little easy. So with aluminum, you find it on the periodic table. Okay. First thing is, what's the previous noble gas? Neon. So it has all the electrons that neon has. So I'm going to put neon as the shortcut. So I got Al. It's got 10 electrons just like neon at the end of the previous shell. You want to say? Aluminum is in the third. Right? And when I count through the S zone, 1, 2, electrons that are in the S, then it skips straight across. And this is why the D's don't appear to me. Okay, well, this is why. Remember, you go straight to 3p. And there's only one electron in this p zone, right? Yes. Okay, that, all you have to remember is S, D with a -1 for those, P's, and then -2 for the F's. That's what you do have to commit to memory without the chart. So we've done aluminum, right? We got it down. I'm going to copy and paste them on. Oh, wrong thing. Why can't I grab what I want? Okay. Fine. Okay. So there's our aluminum's electron configuration. Now we're going to do bromine. Okay. I'll do it with you. So bromine, come on. We're in. Here's bromine. Okay, you guys coach me. How do we start? They are perfect. You're right. Level 4, so 4, and there's 2 S's, and it's like a square, 2. 3D. Actually, if you count across, it's 10. Always.
Oh, wait, so that's the one that's mine.
Yes, the colors on this periodic table don't. Yeah. 3D 10.
So the only minus is the number in front.
Front number only. Oh, right. Yes,
Okay.
that's true. And then the P zone is back to 4. P in this 5. Perfect. You got it. Boom. Right on. Actually, it's our next one. Well, you look while I copy and paste this one. So radon is Rn. You're going to find Rn. It's a noble gas. That might help you out a bit. Yeah, right there. Pointing up. My board is stuck. Let me just pause. Okay. It was pointed out that radon is right here. So oh, I'll shut up. You guys tell me. Shortcut. Start with that. It adds all the electrons that the previous noble gas had. Can't use it as its own abbreviation, which is actually xenon. Then radon is in the 6p, and then 6. No, sorry, you're skipping it. 6s. So we count from left. So the 6s zone. There's 2 electrons there. Then remember that these go through here, and then we come back to this. Okay? There's a space there. We use 14 of those. Your periodic table, I think, is organized better. Right? Yeah, but your periodic table actually has 14 across on the F. Doesn't it? Count. So it's not so confusing. That's why this. Okay, so what do we do for the F's then? What do we write down? Times 2. 4 F's, and we count across 14. That's a memory aid, and we won't get it on down to. If you count across how many electrons, That's where my blue arrow.
Yeah.
Okay, and then we go across 10D things. Front number for the D is always one less than the row number. So 6 minus 1, so 5, D10. Then finally, back to 6, but the P's are 6 across. 6, P, 6. Anytime you end with P6, that's in the final column, the 18th column. Well, actually notice though that all of these line up, the periodic table lines up with the electron configurations very well. So I'm going to just mention something. Third page. So all of these end with P6, different rows, but they have a complete set of electrons in their level. All of these end with P5, and they actually make similar molecules because of that. So on. All of these have, say, S2, actually, this way. Okay, electron configurations. Well, we'll get back to this, and I won't explain it. So radon, I guess I already erased it. Help me out here because I'll put it down. XE, 6S2. Yep. Yep. There we go. Okay. So, shouldn't surprise you that I'm going to ask you guys to do this. But then, one extra thing. After we do this, we're going to figure out this thing called number of valence electrons. So first, just do the electron configurations, one thing at a time. I'll pause the video. You guys come up with the answers for those four. And we compare answers. Let's see. I'm looking nitrogen, helium core. And the outer electrons, we're worried about nitrogen 2s2, 2p, 1, 2, 3. Iodine. Krypton has all the electrons that krypton has, and then iodine is 1, 2, 3, 4. Count over. Iodine. We now get into the. But I periodic table isn't done enough. I didn't count them. Did I? 5. 1, 2, 3, 4, 5. No. 5 is. Subtract 1 for the D's, so 4D, count across it is 10. And then we keep on trucking to 5P. And it's 5O. And uranium is dropped down in the bottom there, F zone. Uranium is Rn, is an abbreviation. All the electrons that radon has, it is in the 7. If we scooch down, and since we dropped down 2 times, you can take that as a memory, 5, F, 1, 2, 3, 4. Okay. This is an example where if you looked up uranium and Googled it up, the electron configuration of uranium, you get something different. Like they said, we're just working on the patterns predicted electron configuration. I'm not worried about this offset thing and that. It isn't actually the electron configuration, but I'm not going to get into why. Okay? But this is why I was saying, don't Google up all your answers. Because this is the one I'm marking correct because I want to see the method, not the actual one. So, chlorine. Okay, chlorine. Previous noble gas has all the electrons at neon. Chlorine is in the 3rd row, so 3s2, count over, and then 3p5. Now, I also said the number of valence electrons, and we haven't figured out what valence electrons are yet. So, we're going to go to the next page and then come back to this and finish the valence electron. Okay? Next page. Lewis diagrams. Well, they show valence electrons. So what are valence electrons? The electrons in the outermost s and p orbitals. In non-metals, valence electrons tend to be the electrons involved in chemical bonds. And they're more useful for non-metals than they are for metals. And things in the diesel, like iron and gold and stuff like that. So I don't ask you for Lewis diagrams and valence electrons. Valence electrons are basically for the right-hand side of non-metals. Okay? We only count the S's and P's. Because for the kind of bonding that the non-metals do for the example B's principles, that's all we really use. We ignore the D's and F's for Lewis diagrams for valence electrons. Okay? So I've got an example here, and then we'll come back to this. So there it is. You never hear about tellurium. I chose it. Anyways, here's its electron configuration and diagram just above. Okay. You ignore the D's, and if there was S, you ignore them. So I say, how many valence electrons? How many S's and P's in the topmost row? It's highest, outermost. And there's 6. There's 2 here and 4 here. Okay. This is going to be pretty easy. How many S's and P's that we listed here? So valence electrons. I'm going to let you guys tell me. Don't count the D's or the F's here. So how many VE here? How many valence electrons? VE here. Valence electrons. Okay. You guys will tell me. I'll just wait and we will see. Pretty easy now. Go and check the second one. I think I heard the first one was correct. Yeah, iodine. Yeah, look at the S. Okay. S and P's. 2 plus 5. 7, 6, 7. Oh, I think I heard 6. Again, I just misheard you. Yeah. Due to my colorblind. Okay. 5. You would, if anyone would be sympathetic to me. So 5. 2 plus 5. P and S is added together. 7. Uranium, only 2. I don't care about the F's. And then lastly, 7. Now, valence electrons, you don't actually have to do an electron diagram to do this. We can figure out the valence electrons because the S's and P's, they line up with the periodic table quite well, and there's a shortcut to do this. If you have, and I already sort of mentioned this about the electron configuration, any electron configuration, with the exception of helium, any electron configuration in the 18th column ends with P6. So you know you've got 2 S's plus P6. They're always 8 valence electrons, 18th column. Other than helium, it just has 2 of them. 17th column, they have S2s for sure, and they end with P5. So how many valence electrons in the 17th column? 7. 2 for them. 16th column, P4. So S's and P's, 2 S's plus 16th column, 6. You guys see a pattern? If I say the 16th column, just take 10 off. Right? 6 valence electrons. We don't do valence electrons very often for these, but they're just 2 valence electrons. There's only 2 S's. But I'm not going to use them to do Lewis now. I can ask you the number, and you just say 2. Okay? So, getting back to the lesson at hand. Valence electrons. They're the ones that are involved with bonding. And I forgot to, and I will now. Let's see here. There it is. There we go. Lewis diagrams show an atom's valence electrons, and that's it. We don't in chemistry really don't care about the inner electron when it comes to bonding. They're easier to use than Bohr diagrams. And we'll do by example. Show you. So phosphorus as a Bohr diagram. Well, I'll do it by video too. Here's phosphorus in a Bohr diagram. I would say first column, 1, 2 electrons, right? And then the next column is 8. Or the column, I said that row. The next row, there's 8 electrons. And then that corresponds to the second ring. The third ring corresponds to the third row, 1, 2, 3, 4, 5. Bohr diagrams don't really worry about whether they're S and P's, but that's all there is. So 1, 2, and I know we double up only 8, but I can do single, 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 and then double them up. So it turns out to be 4 pairs. And then the last one has 5. So this is where it's really important. Single, 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 that's 4, then 5. Now, that's the Bohr diagram. The Lewis diagram is way simpler. It's essentially like our electron configuration curve. We assume that all the inner rows are taken care of. We only put the outermost valence electrons. We never worry about D's or F's. Okay. So phosphorus, I just want the outer row. So really all you look is on the periodic table, I see phosphorus is the 15th column. How many valence electrons? Take off 10. 5. By the way, if I ask you for magnesium, how many valence electrons? It's just 2. There's no 12. Okay. And P, the valence electrons only works for the P block, right? Take off 10. You're not late gaming or something. So much love here. Okay, so 5 electrons. 1, 2, 3, 4, and then we double up. 5. I want you to imagine when you're doing this, it's like a rectangle around a letter. Like have 4 sides when you put this in. You keep them flat. That's disappearing. Do not, and I don't like showing mistakes, but do not have the electrons scattered or evenly spaced or anything like that. Okay? So fluorine. Fluorine is in the second row, so it's only going to take 2 rings. Everything that's contained in the first ring for the Bohr diagram. 1, 2. And then in the second ring, second row, 7. So 1, 1, 1, 1. So single, 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 single. All the single letters. 5, 6, 7. Ever heard of Beyonce? There you go. Should look like that. I know a lot of people said they prefer my version. This is the first time I ever sang it. Nobody said it. But I was hoping Katie would say something else nice about it. If you told me I was boring, that was really nice. Okay. Working out the exceptions for these as far as 4 sides, and basically Lewis diagrams want 8 electrons to fall, with the exception of hydrogen, because there's only 1 electron. And then helium, it's like the first ring of the Bohr diagram. It's 2 electrons, and they come as a pair, don't single, single. Singles. I think like single cheeseburgers get lonely sometimes. That's why I order doubles all the time. Yeah, reunite with my son. All right. Well, a little bit more. You guys have this on your handout? No. Well, don't you worry then. I'll get it to you next week. Or next, right? Come on. You wanted an assignment. I had it, and I forgot to pick it. I thought he did. My mistake. Good teaching. Okay. Any more compliments for me? Okay, octet rule. Octet, 8 octopus, 8. Where we're at. You can already see here. This should be kind of reviewed. I'm going to pause the video while you jot down what cations and anions are, because I'm going to print this thing just for Katie. Well, actually for everyone. What we have here is this idea of 8. And I've already mentioned atoms tend to lose, gain, or share electrons in order to get a full set of 8 valence layers. Hydrogen and helium are the exceptions. Just 2. Transitions metal, we don't even worry about them. Ions, that's what's created when you gain or lose. That's a review from grade 9 or 10. Cations, we say, are positives. They've lost electrons. Anions are negatives. They gain electrons. Predict the charge and give a Lewis diagram for the following. Sodium and a sodium ion. So what I want you to do is write down a sodium atom. And sodium, and look up, oh, it's in row 1, so it'll have 1 dot. Right? Okay. So you're going to do this. You're going to write that down and then the sodium ion. Down, right? What is the sodium thing then? Any with the dot. Oh. Okay. So then sodium ion. Something screwed up on my board. You can see it. Sodium, same symbol. But here's what we say on the periodic table. What's the closest noble gas? Basically, neon goes backwards. So in order for sodium to have the electron configuration like its closest noble gas, neon, it has to lose 1 electron. It'll be +1 because it's lost a negative electron. But it has no electron. This is the diagram. Now, I'm going to put it in a bracket here just because I'm thinking it's a diagram, but it's got no electrons. I don't really need the bracket. Yeah, it is. But that's why it's a plus, because it wants to be like its closest. Now, we're not going to do a million. Now, in an atom of oxygen, 16th column, so O with 6. 1, 2, 3, 4, 2, 5, 6. Oxide ion, though, we know that the charge on an oxide ion is 2 minus. But I'm going to put this one in brackets, and the brackets make sense here. Oxygen. The closest noble gas is neon as well. It needs to pick up 2 extra electrons. You see all these? Okay, I'll just draw one and start. Now, I don't need to use an extra different color, but this single spot here fills in. This single spot fills in. Do it in the same color, but I just want to emphasize this is what's going on. Okay. An atom of oxygen and the oxide ion. This is where you need the brackets. Yes. The ones I give, yes. Now, this explains our ionic compounds that we have sometimes. Ionic compounds are formed between cations and anions, usually metals and nonmetals. Predict the formula of an ionic compound of sodium oxide. Now, we already know Na plus O2 minus. We can do it this way. So we know this, and I hope you've known this since grade 10. Okay, crisscross applesauce, you have to have as many positives as negatives, Na2O, right? But as far as a diagram, see if this makes sense. If I have sodium, and we know it's 2Na, and I put this sodium as an atom, not as an ion. Then I have oxygen. Oh, what am I doing? Okay, these are what we have from above, right? When they come together, sodium plus oxygen, the elements, what happens is that the oxygen needs the extra electrons. The sodium wants to lose them to have the more stable electron configuration of the closest middle gas. So, in a sense, a sodium electron's transferred, and another sodium electron's transferred, and that's how you end up. Follow that? Yeah. But this is what we're really in there. I gotta guess. I just drew wavy lines for fun. That's where we're gonna leave this. I'm gonna run and get that evaluation. I'm not gonna give it to you right now. I don't have it ready